Okay, so today we're going to jump off of what... Oh, thank you. Thanks for telling me early. That's good. This is when I need to tell the jokes. Okay, now let's try this. All right, good. All right, so jumping off from what we did last time, where we started talking about vibrational systems. So we went from the particle in a box and particle in a ring, these one-dimensional systems, and then I connected that to the vibrational wave function, which is also a one-dimensional system. So I wanted to go ahead and branch out and start talking about vibrational spectroscopy. So we're going to talk about the spectrometers that we use for vibrational spectroscopy, and then we'll get into the theory and we'll actually do some calculations with Gaussian. So we'll start looking at the vibrational spectroscopy. That's probably the most useful spectroscopy that we have for identifying molecules, atoms, and ions because of the vibrational way that they display. So if a molecule is bonded in even slightly different ways, you're going to have different vibrations. And so it'll have a different infrared spectrum. In fact, we call that a fingerprint. So in organic chemistry, you're taking a survey of organic and you get into infrared spectroscopy, you can identify some things like the CH stretch region or the carbonyl stretch and so on. But then this whole middle part where all the bends of the molecule occur, it's so complicated that we just say, that's the fingerprint region. That it just tells you what molecule you're dealing with, but identifying each individual peak is difficult. But for small molecules, it's not that difficult. And if we use Gaussian, then we can identify every little bump in the spectrum. And so we'll look at that today. So this is what we're dealing with, vibrational motion. Now this is an incredibly simple system that I've shown here because it's essentially two atoms, one vibrating with respect to the other. I wish this little picture showed the heavy atom at 0 and the light spot moving, because like in HCl, hydrochloric acid, gaseous HCl, the chlorine is so much more massive than the hydrogen. It's essentially the hydrogen moving, and the chlorine doesn't move very much at all. So this picture that I got off the internet is just not, I wish it was reversed. Okay, so yeah. So that the green atom was the chlorine and the hydrogen was the thing that's moving. But anyway, the idea though is that this is harmonic motion. This is like a mass on a spring. And it's, if you let your mind think about it too long, it will break, okay? Because we're using the math of massive objects, things you can hold in your hand and weigh on a scale. The harmonic oscillator, we're using that math to model vibrational motion, which is being governed by a wave function, okay? So once again, we have this idea. We have a classical model of a mass vibrating on a spring, and that math fits our spectroscopy really well. But when you get down to it, the behavior down in this bottom energy levels is the wave function behavior. It's very similar to the electron on a wire. It's an oscillating wave function. It's not a mass moving back and forth. But we can use this analogy of a mass moving back and forth to understand some of the things related to vibrational motion. If the mass is heavier, the frequency is lower. If the spring is tighter, the frequency is higher. So those kinds of things will work for your thinking in terms of vibration. And so this is how we measure vibrational spectroscopy. This is a common spectrometer. This is using a attenuated total reflectance attachment. So we have a hot source. This is, any hot object can be a source. We have a ceramic resistor that we run a stable current through, and it heats up and gives us that black body radiation. So at whatever temperature we have this nice black body curve like that. And that's what's coming off of this hot ceramic source in the infrared. Then we take this through, in our modern instruments, we use an interferometer. And so then this light coming along, like if we had plain polarized light, would split, and some of it would go this way, and some of it would go on this way. and we move this mirror back and forth, and we create constructive and destructive interference at the beam splitter. So this is a Michelson interferometer that I've shown here. And so then that light is sent through our sample. So this here produces what we call an interferogram. So you have this big center burst. So we have intensity versus distance, and the scanning mirror is moving a distance, left and right. And this distance is typically measured in centimeters. And when we have no sample there, we get a picture of that interferogram. And we can take that and we can go into the electronics where we do a fast Fourier transform. And what this gives us is an inverted x-axis. Okay, so notice up here our x-axis was distance or mirror displacement in centimeters, and our x-axis over here now is in inverse centimeters. So we get wave numbers out. And so we end up with the various peaks that we have, okay, in our spectrum. And then we take our incident, like without a sample, we take our single beam background, and then we put our sample on here. And we take a reference and a sample spectrum and compare them, and we can plot that minus log of I divided by I naught, and that gives us our absorbance spectrum.
So I don't think I quite understand the point of the scanning mirror still.
It's let's see, I have a slide on that in a different PowerPoint, but what it does is it's taking this beam that goes off to the moving mirror, and it starts to move. Now it's going to be frequency dependent, or let's say wavelength dependent, that distance. And so it's going to go down to that mirror and come back, and it's either going to cancel out that frequency or merge back with it. So think of it, half the light goes forward, the other half goes to the right. And by changing the path length of the one to the right, we select various frequencies at the beam splitter. And so just changing that distance a little bit can cause some of those wavelengths to cancel out and others not.
Okay.
And that's where we got this interferogram. So when it's in the center, then none of the wavelengths are canceled out. And so that's why you get this center burst here, where it's exactly in the center, the path lengths are the same, so the light goes same distance left and up, and comes back, and all of the wavelengths, regardless of wavelength difference, they all constructively interfere and come out of the interferometer. But as you move that path, you select certain frequencies to be interfered out.
Yeah.
And you're sending that pattern through your sample. Now your sample, if there's no sample, then you just get the spectrum of your source. But you put a sample in there, and your sample takes out certain frequencies. And then the Fourier transform is able to turn this distance-related interferogram into an inverse distance or wave number-related spectrum. Now, we do this also in NMR, but we don't do it with distance, we do it with time. So in NMR, we pulse all of the protons in the sample in this magnetic field, and then they precess around that magnetic field at different frequencies. Okay? And so we're measuring versus time, and we're getting the signal of those protons as they go by. We're able to measure their, the nuclear spin difference in this magnetic field. And as they go along, we get a signal, a radio frequency signal. And so NMR takes this signal like this that tapers off. And it's like 1/2 of this interferogram. In infrared, we take it versus distance. In NMR, we take it versus time. And then we do the FFT, the fast Fourier transform, which again inverts that x-axis. So we have intensity now, not in terms of time, but in terms of inverse time, which is frequency. And so we end up with a spectrum versus seconds to the -1, or frequency. Okay. So this is, I guess, the point that the fast Fourier transform is takes that intensity that was a function of a certain axis and inverts that x-axis. So you can go from time to frequency, or you can go from distance to wave number. So, and then you can get that for the source, and then you can get that for the sample, and take the difference, and you get your absorbance spectrum or your transmitted spectrum. Now, the reason what makes this spectrometer a vibrational spectrometer is the infrared, the mid-infrared. We could do this for UV vis. We could do this, obviously we could do it for NMR. There's nothing special about this interference technique or the fast Fourier transform. But for vibrational spectroscopy, we have the Fourier transform infrared spectrometer. So, well, let's talk a little bit about this ATR, this attenuated total reflectance attachment. So you can think of this kind of like a trampoline. Do y'all know a trampoline, right? You've got these little springs that hold this. I'm doing my best. Okay. Okay, so that's a trampoline. Do you see? Can you see it?
Yeah.
All right, you got a little kid jumping on here.
The kids are sample.
Yeah, the kid's our sample. He's jumping along. Okay, and where does reflection take place? This is sort of stepping back. When light reflects off of something, where does it take place?
Between where the refractive index changes.
Yes, very good. So if there's a change in refractive index, that's the membrane, if you will, that's causing light to reflect. And if the bigger the change in refractive index, the more probable a reflection. Like I can see my reflection in this glass. It's transparent, but there is a refractive index change from air to plastic. And so there's some reflection off of this plastic that I can see, okay? If I have a really dense material that has a huge refractive index compared to air, I can get a lot of reflection. And if I pick a particular angle, I can get 100% reflection. And so diamond to air, diamond has a refractive index, I think it's 9, 8 or 9. It's huge. And air is slightly more than 1, right? And if I pick an angle here, I can bounce 100% of my infrared light off the bottom of that diamond. So think of this light as coming up underneath here and hitting this trampoline from below and coming out 100%. Okay. And that's why we call it total reflectance, total reflectance. So it's at a certain angle to the infrared light. It's going inside this diamond crystal, and it's this is the diamond here. It could also be germanium, but we use diamond. So it's going in the side of the crystal, bouncing off the inside surface of the top of the crystal and coming out the other side. You could use germanium too. That's a common one. Silicon maybe, but diamond's harder. And it's better for educational institutions because you never know what the students are going to do to your sample holder, right? And so, if they, like I've done studies on asphalt where they just let asphalt cure on the diamond. Right? And it's no big deal. You just scrape it off with a Brillo pad because diamond's harder than the metal. So the metal's not going to scrape the diamond. The diamond's going to scrape the metal. So that's really great. Diamond is great. Yeah. Now, it's not a gemstone. Don't go steal my diamond, okay? But it is a diamond, you know. It is somewhat valuable, but it's not very pretty to look at. It doesn't have the facets. And the reason we cut the diamonds that way is because not only does refractive index cause reflection, so it sparkles, but it also bends light. Refraction is increased with refractive index. And so in the given path length through the diamond, the red, green, and blue wavelengths of light are going to separate more than they would in glass. And so that's why the diamonds have such pretty colors. Glass has colors too. You can have glass crystal, but you need a bigger piece of glass to give you the same separation that you get out of a diamond. So that's why diamonds are so valuable in terms of jewelry, is because in the small gem you get beautiful green, red, blue colors coming out of it because of the high refractive index. So anyway, just gee whiz type stuff. So now if you put a person or a sample on top of this trampoline, when that light is reflecting, it's bouncing the surface a little bit. And the sample, if it matches one of those bounce frequencies, can absorb steal some of those photons. And that's the attenuated part. This attenuated.
So that would change the wavelength that comes out?
It takes away certain wavelengths.
Okay.
It changes the transmittance.
Yeah, the transmittance and the absorbance. So if we plotted absorbance, then we get a peak where the missing light was. So the sample's sitting on there, the trampoline's bouncing, and the sample takes away some of those frequencies.
But no energy. So energy's conserved.
No, it goes into the sample. It says 100% are total reflectance, but it really isn't total. It's attenuated. So if you take the sample off, you say 100% is reflected. You put the sample on, some of the light's missing. Yeah, at certain frequencies. And those frequencies happen to be in this infrared region, with the infrared source, some of those frequencies are missing because of the vibration of the sample. Now the path length, the real issue though is the path length is not constant. So path length, it's really kind of, I'll put path in quotes because it's really not a path through the sample. It's an interaction depth is really what we should say, but it's frequency dependent, which kind of stinks. So if we have 4,000 wave numbers here and say 400 here, the curve looks like this. And so, you know, this might be way over here, 2 microns, and down here might be 0.2. So at the low frequency side, it's interacting with the depth of the sample up to like 2 or 4 microns. So it's pretty deep into the sample. But over here at the at the CH stretch region, you know, 3,000, 4,000, it's only 0.2 microns. So very shallow depth. And what that means is you have very small peaks at this end, you know, so because of the path length being, you have really tiny peaks. And down here, you have really strong peaks. Because there's, again, this absorbance or this signal strength is proportional to path length. You know, Beer's law, right? Absorbance equals the absorptivity and the path length and the concentration. And so if you have a bigger path length, you have bigger peaks. And so this is a little problem. Our Beer's law equation is now frequency dependent. It changes whether it's at the CH stretch region or the down here at the like heavy atom stretch region or bending. And so what you need to do if you're going to match these things to a library is you need to use the ATR to collect your library samples too. And so you need to compare apples and apples. So if you have a library that's ATR spectra, you need to use an ATR attachment to match with that library. If you have a transmission, like transmission cells for all your infrared, and you're using an ATR for your sample and you're trying to match it to the library, it's not going to be a very good match because the CH region is going to be small and the bending region is going to be big, and your library is not going to, have the same relative intensities for those things. So let's look at the phenomenon in the molecule, what's happening in the infrared. Now, this is something I tried to make, at least for the book that I'm writing, all of the quantum numbers in my book are N. I just picked N as a quantum number throughout the whole book. But that's really not accurate in science. I mean, for vibrational motion, the quantum number is V. Okay, so it makes sense, V for vibration. And so in this set of notes here, all of the quantum numbers for vibration are V. Okay, for rotation, they'll be J. Okay, but in this case, we're just talking about vibration, and so we have V. Now, we only had one coordinate in our particle in a box. We had the x-axis. Okay, and so we just had one quantum number, and that was it. But in vibration, we have a lot more than that. So let's talk about the total degrees of freedom. This is everything a molecule can do. And so you have, let's take water for example. So I've got an oxygen atom and 2 hydrogen atoms, and each one of those can move in the X or the Y or the Z direction. So every atom has 3 things it can do. And that's what we mean by degrees of freedom. 3 independent things. I can move the oxygen atom in the X direction and leave the hydrogens alone. So that's an independent degree of freedom. I can move it in the Z direction. I can move it in the Y direction. So every atom has 3 degrees of freedom. And so that's the total degrees of freedom is equal to 3N. And N equals the number of atoms. Okay. Now, if all 3 atoms in water are moving in the X direction, we call that translation. So the whole molecule is moving because I have an oxygen and 2 hydrogens, and it's moving in the X direction. So one of those degrees of freedom is actually translation in the X direction. What if they were all moving in the Y direction? Again, that's one of the degrees of freedom is translation in the Y direction. And if they all move in Z, then that's translation in the Z direction. So there's always and only 3 translational degrees of freedom. Even for DNA, with hundreds of thousands of atoms, they can all move in the X direction, and there's only 1 translation in the X direction, only 1 in the Y, and only 1 in the Z. So there's 3 translations. And then I don't know how to do this for DNA, but for water it's easy. I kind of leave the oxygen alone, and I take this hydrogen and move it in the positive X direction, and I take this hydrogen and move it in the negative X direction. And if I want my molecule to stay intact, they have to keep the same bond length of oxygen, so that's rotation. And so that's rotation around Z if the atoms start moving in the opposite direction on X. And so that's a particular degree of freedom that is just rotation around Z. Well, I have 3 axes, and so I could do the same thing around Y and the same thing around X. But there are no other axes for the molecule. So I only have 3 rotations. So 3 rotations.
And that's also for every atom? Or for every molecule?
For every molecule, yeah. So even in DNA, it'd be hard to figure out how much. It's kind of like an impulse, like I punch those atoms and create the rotation. So a little impulse vector on all those atoms in opposite directions around a central axis, and then the thing can rotate. But it's governed by the number of independent axes you have, and we just have a Cartesian system of X, Y, and Z. And so that's where we get our 3. It's the cardinal directions, the Cartesian directions, X, Y, and Z. So they give us the 3 rotations and the 3 translations. So that's those are not vibrations. Those are rotations. Those are translations. Everything else is a vibration. So if I've got water, and these are the 2 hydrogen atoms, and now instead of going in the same direction in Y, they go in opposite directions in Y, then I have a bending motion. So So the hydrogens are bending like this. The molecule's not moving in space. That would be translation. So the center of mass doesn't move. It's just the hydrogens do this. And so that's a vibration. And I could go through and add up all of the ones, but I know that there's going to be 3n here, the total, minus 3 translations, minus 3 rotations. So 3n minus 6 vibrations. Okay, so for water, there's 3 atoms. So 3 times 3 is 9. So 9 minus 6 gives me 3 vibrations. Okay, and if my head is the oxygen and my hands are the hydrogens, this is the symmetric stretch, this is the asymmetric stretch, and this is the bend. Yeah, I like the asymmetric stretch.
Yeah.
My water dance moves. Yeah. So that's it. Those are the 3 vibrations that water can do, and they add up to the 9 total degrees of freedom: 3 translations, 3 rotations, and 3 vibrations. Okay, but you get to a bigger molecule, and it gets way more complicated. But there's still only 3n minus 6. So this is actually a spectrum of acetonitrile that I've got here, a part of it. What does that mean to have 3n minus 6 vibrations? We have 3n minus 6 wave functions for vibration. We have 3n minus 6 quantum numbers. Okay, that's the key there that you got to get into your mind. We have that many quantum numbers. 3n minus 6 vibrations means 3n minus 6 quantum numbers. And 3n minus 6 wave functions. So this particular slide I have, notice I've got this right here, these 4 zeros. That's sort of a designation of the 4 quantum numbers. V1 is equal to V2 is equal to V3. All of them are equal to 0. And so the reason that the infrared spectrum is so complicated is because we have all of those wave functions and all of those quantum numbers. And so this might be here what we call nu 1. So excitation to the first vibrational frequency, where V1 equals 1 and V2 and 3 and 4 are still equal to 0. So this is the fundamental for wave function 1. Okay, so it's going from 0 to 1 for wave function 1, and all the others are still in their ground state. So this is a single molecule that has lots of quantum states, and all of them can be in the ground state, or one could be excited while the others. Think of a guitar. I can play one string at a time, right? Mm-hmm. Or I can play all the strings, but each of those strings has a quantum number. So this is just one of those strings being plucked. And it's that vibration, and it's excited now, and the others are in their ground state. Okay, yeah, so you have 3n minus 6 strings on this guitar in the vibrations. Okay, and so we could label that to say, like, string 1 is vibrating at an excited state, and the other strings are vibrating in their ground state. Or we could do this one, string number 2. So we call that nu 2. That's the fundamental for nu 2. So nu 2 is equal to 1, and the others are equal to 0. And that is got a different motion in the molecule, different atoms are moving, different bond strengths, different force constants, and so it has a different frequency. And so it shows up at a different place in the spectrum. Notice these are the energy levels. So this is the energy energy 1, so this might be energy 2. Energy 3, energy 4, E0 for everything. And so the spectrum are giving us the spectral lines, which are the differences in these energies. And so this peak is showing up here with this difference at, looks like 750 wave numbers. right? And that's what puts it right there on the spectrum. Whereas this difference here is at like 910. And this difference here is like 1050. And 1380, I don't know. So where this molecule is being excited, that's where that difference shows up in the infrared spectrum. Now, the confusing thing could be you might have, I don't know if I want to get into this just yet, but let's see. Yeah, we'll talk about that later. This is complicated now. I was talking about maybe doing a combination band, but we'll add that complexity later. So are there any questions or things I can clarify related to this figure? Because this, conceptually, this is a really important thing for you to visualize. When you're looking at an infrared spectrum, you need to be thinking about these are all of the changes in the vibrations of the molecule.
Okay. Now, you wouldn't get any of these added together to form a peak. Like you want to take you can't get the.
Well, you could. That's kind of what I was thinking of doing. If we did, say, let's go up to a level here, right here, that happened to be nu 1 plus nu 2. So this level would be labeled 1, 1, 0, 0. So look at my quantum number designations. I've gone from 0, nu 1 would be this 1 in the first slot, nu 2 is 1 in the, so I went from 0, 0, 0 to 1, 1, 0, 0. Now that can happen in a molecule. It's called a combination band. And so you've got your guitar and now two strings are hit at the same time and they're oscillating with each other. Okay.
I was about to ask that question. Is it possible for the four states to vibrate at the same energy level?
If they vibrate at the same energy, they will have the same, like it'll be degenerate. So they would be, I guess, like you might have a degenerate mode, like nu 1 and nu 2 might actually be the same energy, like in CO2, the bending motion, it can bend in the Y direction, it can bend in the X direction. So there's two energy levels there, but they have the same frequency. Yeah, so they're doubly degenerate. If we had this combination band, you would see a peak here. Okay. And I guess the reason it makes it complicated is because this peak is here, but there's really, you would have to draw this energy level and have to designate it with this particular designation of a 1, 1, 0, 0. So every energy level in the molecule will have this sort of serial number of its quantum states. And we're used to these kinds of complicated quantum numbers. If you think about the atomic orbitals, we have the principal quantum number, N, we have the angular momentum quantum number, L, then we have the magnetic projection of that angular momentum quantum number, the M sub L, and then we have the electron spin, M sub S. And so there we have four quantum numbers to describe every energy level of a particular electron in an atom. And we just chose to put letters on some of those to make it easier. So we have, the 2p 0, spin up, and so then you have a particular electron that's described by N equals 2, P is L equals 1, okay? And then the 0 means M sub L equals 0, and spin up means M sub S equals 1/2. And so we have 2, 1, 0, 1/2. We have lots of numbers associated with that electron. And this is the same in the molecule. We might have this motion here, and that's given a particular vibrational quantum number. So that might be 1, 0, 0 for that particular vibration. The only time this really becomes an issue is if you're trying to assign the spectrum and put quantum numbers on every peak. Most of the time we don't do that. Most of the time we just go to the library and search and see what the substance is, right? But if you want to use spectroscopy to learn about the molecule, then you need to assign the spectrum, and you need to like assign the quantum numbers to the peaks. Okay. Is everybody okay with direct absorption? Arrows are going up. You could have emission, but infrared emission is not very common because you're in the thermal region of the spectrum, and so the background noise is pretty bad. We have lots of infrared photons running around from every heat power supply that we have. And so there's a lot of background noise trying to do emission in the infrared, but it can be done. It's how our night vision goggles work. So we're looking at the emission of infrared light from hot objects like human bodies and motors and engines. Yeah. So let's go to scattering next. So Raman spectroscopy is a 2-photon process, as we've talked about. And so we have Rayleigh scattering and Raman scattering. Rayleigh scattering is if there's no change in the frequency of light. So the incoming photon leaves with the same frequency, same wavelength. This little dashed line is not an energy level. It's just showing the oscillation of the electron cloud. And it's just kind of showing sort of an aid in showing that this arrow up matches the beginning of this down arrow. Now, if you have Stokes shift, this might be 0, 0, 0, 0, and this might be 1, 0, 0, 0. So that would be the fundamental transition for V equal V1. If you have molecules that are already excited, then they can de-excite with this Raman system or Raman phenomenon and give you a blue shifted light. So, wavelength could come in and leave with a longer wavelength, right? Or the incident photon could come in and leave with a really short wavelength. Yeah. And so we have these symmetry elements that we can look at. So direct absorption and emission is governed by this transition dipole moment integral, with X, Y, or Z used as the dipole moment. So this is the transition. And that's what we saw for the particle in a box. But for Raman transitions, they're not the dipoles, they're governed by the polarizability operators. And these are all second order in our Cartesian systems. You can kind of think about this as the incident photon, so like incoming on X and outgoing on Y, or incoming on X and outgoing on Z, or incoming on Y and outgoing on Z, or coming in on X and leaving on X. Okay, so you have all of these 2-photon processes that are governed by 2 Cartesian systems, either the same one squared or some combination. And so here's an example of the Raman scattering and Rayleigh scattering. I put these up here just to kind of show you that these are really long arrows. So this is typically visible frequencies. And of course, these differences here are so we're getting vibrational information using visible light. That's fantastic. That can't be overstated because it's a real pain to deal with infrared light. So if you go to my spectrometer and you look at it carefully, the windows, they look like glass windows. But over time here in Huntsville, they will get foggy, okay, because it's so humid here. So the moisture in the air is attacking my windows and will eventually ruin them. Okay, we have to use salt optics in the infrared, and that's not very convenient. In fact, there's a funny story a friend of mine told that he went to Wichita State and they had, they did infrared spectroscopy in their lab, and they had a gas cell and with salt windows, and they were kind of foggy, and he thought they were dirty. Okay, so he put them in this cleaning bath. called a base bath, right? And they dissolved, like they're gone, and no window left. Okay, and they're in group meeting with the advisor, and they're just chit chatting or whatever. And he said, "Hey, whoever took the salt windows out of the base bath, I need them. I was cleaning them for my experiment." And before anybody could say anything, the advisor chimed in and he said, "Hey, wait!" He says, "You're not going to graduate till you find those windows." And the guy was like, "What?" He said, "Nobody say anything. You find those windows and you can graduate." Okay. And so then later on, he figured out what happened. He's like, "Oh man, they dissolved. What am I going to do?" And so he got on the internet and he ordered some more windows with his own credit card. They're $100 or so, but he told his advisors. He said, "I found those windows," and his advisor said, "How are they?" And he said, "They're like new." So he was able to graduate. But for visible lasers, you can use glass. And so we can collect our vibrational spectra through glass vials. And also we can use lasers, which are directional energy. And they have a very low divergence. I mean, they do spread out over distances, but not very much. Not as much as like an infrared beam. So Raman spectroscopy has been really useful for things like combustion research. Because you can take a jet engine, and you can send the lasers through the flames in that jet engine and look at the efficiency of combustion. And so a lot of the combustion research was done with Raman spectroscopy. So they're doing vibrational analysis in the flame without ever having to touch it. So that's really very cool. So you can send these visible lasers through your sample, and it's the difference. It's the difference in your incident light and your outcoming light that gives you the vibrational difference. So this difference here is nu 1, and this difference here is nu 2. So the vibrational frequency of that second vibrational mode. And if you plot those as a difference from this Rayleigh line, so notice the Rayleigh line is got 0 difference. That's going to be your laser wavelength. If you plot the frequency difference from that laser wavelength, then this is at vibrational frequency 1, this peak is at vibrational frequency 2, and so on. So let's look at these on top of each other. This is the way the Raman experiment works. We use a laser. We blast the sample with a lot of light, billions and billions of photons, and only like 1 in a million or 1 in a billion will actually be scattered in a Raman situation. Most of it's scattered in Rayleigh light. So we use a prism, we throw away most of the laser light, we throw away the Rayleigh light, and we look at the small amount of photons that are scattered in a Raman process. So here's our spectrometer. We have the laser, we have the spectrometer, and we have the sample holder. And we use a fiber optic system. It's pretty convenient. In your research too, if this is going to be useful to you, then it's definitely open for use in your research. So here's the overall spectrum showing both Raman and IR on top of each other. So this dashed spectrum here is the Raman, you see? This top one is the IR. And then I have the Gaussian simulations of the IR and the Raman here as a stick spectrum. And look at that. That is pretty amazing. Gaussian is pretty accurate in its predictions. So these sticks are showing up right where those peaks are. Yeah. So it's pretty amazing. Now, the benefit of using Gaussian is not so much to identify the molecule, but to identify the vibrational modes. And so here you'll see in the notes, of course, in your static notes, they're not vibrating, but in the PowerPoint, I've got them all animated. So way down at this low frequency end of the spectrum is vibrational mode 8, nu 8, and that's a bending motion of the whole molecule. If you're bending the whole molecule, a lot of mass is moving, and bending doesn't have a lot of restoring force, so the spring constant's low. So it's going to be a low frequency. You're moving a lot of mass, and you have a low spring constant. Here's a stretch. Again, we're moving the this is acetonitrile, so the nitrile group and the methyl group are moving apart from each other. So we're moving lots of atoms together. So big mass, a single bond, which is a small spring constant. So it's down here at 900 wave numbers. Here we have a bending motion. And I said bending motions are lower frequency, but it depends on the mass. These are hydrogens really that are moving. And so they're a small mass. And so it can bend at a pretty high frequency. So that's around 1,000. And here's the umbrella mode. You ever get in a windstorm with an umbrella and it inverts? Okay. And then you open an umbrella. That's when the methyl groups are doing this. That's an umbrella mode. So they're expanding and contracting like that. And you can kind of see it on the screen here. This is a deformation mode. So this is the deformation of that methyl group. Again, you're bending hydrogens, small mass, high frequency. This is the carbonyl stretch, or the nitrile stretch, not the carbonyl. The nitrile stretch is in a really strange region of the spectrum because it's a triple bond. And so, but nitrogen's kind of heavy, but the triple bond brings it up above the carbonyl. And then here are the CH stretches. The symmetric stretch is typically lower frequency than the asymmetric stretch. And that's because you're thinning out the electron cloud that's holding those hydrogens onto the methyl group. So as you stretch all the hydrogens out, the electrons are a little weaker and pulling them back. And so the restoring force for a symmetric stretch is a smaller force constant than the asymmetric stretch, which is here. So the asymmetric stretch is a little higher frequency.
That's because it shifts the density of the cloud, right?
Yeah, so you still have that cloud of electrons, and one hydrogen's going out while the other's coming in. And so that's a little higher frequency. Yeah. And so that's, again, showing you all the vibrational modes in this molecule. You might say that I've added it up and there's not 3n minus 6, but all of these E motions are doubly degenerate. And so you can go through and calculate all of those, and you hit some peaks are for both of these motions like this one, and some peaks are just for a single motion. And so you can add it up and you can get, see there's 3, 4, 5, 6, there's 6. So 3 times 6 is 18, minus 6 is 12, and there's 12 motions in this molecule. And this is the spectrum of all of those. So that's vibrational spectroscopy in our instruments, and we'll get into Gaussian next time and start thinking about making some Gaussian calculations. Okay.
Can you go back to that last slide?
Yeah, sure.
With the vibrational 3 plus 4, so that's actually 2 jumping at the same time. It doesn't affect the Gaussian curve. It just, like for the area probability.
Okay, yeah, so we're done. I'll go ahead and answer that question. So the question is, there's different places where Gaussians are used. So the vibration of the ground state vibrational wave function is a Gaussian. And then the shape of this peaks, like if I were to put a Gaussian on this stick spectrum, I'd have a Gaussian curve put on that stick spectrum. Which Gaussian are you talking about?
The combination of 3 plus 4. I was just wondering if it affects the...
Oh, this combination of 3 plus 4. Yeah, so I didn't actually model that in Gaussian, in the Gaussian software. So now that we're clear. Yeah, and so the Gaussian software predicted this nu 2 a little higher than it shows up. And then this 3 plus 4, if I were to figure out what that would be, I would just take the frequency of 3 and the frequency of 4 from my software and add them together and put a stick there.
Okay.
Yeah, but as far as the intensity, I wouldn't know what that intensity would be.
Okay.
So I would just really be looking at the combination location on the x-axis. I couldn't tell you the y-axis. Yeah.
I'll just do it.
No, that's a good question.